Thanks. Yes, so the program of today is that I would continue for a few more slides the discussion that we started yesterday about like more recent developments in X-ray free electron laser science. So yesterday it was mainly on this technique of seeded FELs, right, which improves the properties of the FEL pulses compared to the SASE, the self-amplified spontaneous emission mode. And but yeah, today it will be a few more slides about some new developments, including exciting, a very recent one, which will connect back to the very first lecture that we had. And then there will be a small quiz, question and answers, just like we had before, for you to have a chance to recap a little bit about all this FEL topic. And then there will be the first paper presentation about attosecond pulse generation using X-ray free electron lasers. And yeah, unfortunately, we have only one paper presentation today, but there will be another one on a similar topic next week then. This just for due to some scheduling issues. So yesterday, just as a brief, short recap, yesterday we introduced this topic of seeded FELs, and yeah, the question was, so the main goal is to get rid to like somehow get laser emission not just starting out of the noise in the SASE mode, which produces these very spiky and non-deterministic pulses and pulse spectra, but to start the laser process by a more controlled way. For example, and the best would be just like in various laser systems actually that operate in the visible range. For example, diode lasers can be operated in a seeded mode where you have one very stable first called the master laser that produces a very well defined like narrow bandwidth laser emission, for example, which is then injected into another laser diode that just serves as a laser amplifier. This is quite common in diode lasers. It's quite common to use the seeded lasers technique in for dye lasers. So it is kind of straightforward to try to implement a seeded lasing technique in free electron lasers. Only the big problem is that we are talking about the X-ray range, and there is no like X-ray lasers, even no weak X-ray lasers to start the lasing process in the first place. But as we figured out, one way is to start with SASE free electron laser, which produces these spiky spectra, but then clean up the spectrum by this Bragg diffraction single crystal monochromator here that either transmits only a narrow frequency component to then seed a second undulator, which just acts as an amplifier. Or, yeah, we had this discussion yesterday, very equivalently, we can also use this single crystal monochromator to carve out a very narrow notch in the spectrum, which again produces in the time domain a long but quasi monochromatic pulse component, which by adjusting the timing correctly with the electron bunch then can specifically be or selectively be amplified. And in this way, then we get the monochromatic component that is amplified, and we get a nice and sharp emission spectrum. So that's the self-seeding technique for the X-ray range. In the EUV or XUV, extreme ultraviolet range, there we can apply another technique, which is called the HGHG, high gain, high harmonic generation, And here the trick was that now we actually use an external femtosecond laser. Which is usually just a conventional titanium sapphire laser, but then converted to the third harmonic. Or also quite common is to use an OPA, or optical parametric amplifier, to get tunable seed radiation, which then seeds the lasing, but actually not the lasing, but it is used for uh, energy modulation in a first short low gain undulator. Yeah, so to get energy modulated electron bunches after the first undulator, then using a dispersive section, this is just a magnetic chicane. The energy modulation is converted into density modulation, into micro bunches, just spaced by the wavelength. So actually this magnetic chicane fulfills two functions. One is to do this conversion from energy modulation to density modulation. The other is to induce higher harmonics in this density modulation. So we start out with a sinusoidal energy modulation, but this sinusoidal modulation is not directly transferred into sinusoidal density modulation, but this is like a much more peaked density distribution, which therefore contains, by Fourier transformation, contains also components with higher harmonics, like lambda over n, where n is an integer number. And then the radiator is just tuned to one of these selected higher harmonics. And in this way, we can then scale up the seed laser wavelength to some higher harmonic where n can be up to 15 roughly. So this is good enough to get from the UV, that 260 nanometer is ultraviolet, into the extreme ultraviolet, but not yet into the X-ray regime. Yeah, we discussed all the benefits of that. The only laser so far where this is routinely available is the free electron laser Fermi at Elettra synchrotron facility in Trieste. And yeah, there you can directly switch back and forth between the SASE mode, where you get this typical spiky spectrum, to the HDHG just by basically blocking the seed laser, just by putting your hand more or less in the seed laser beam. You can then have the FEL run either in SASE or a seeded mode. And this technique can be applied even in a cascaded mode or cascaded way, meaning that we start out with a seed laser pulse, have a modulator, a first radiator to get into the 10th harmonic, yeah, from 210 nanometer to 21 nanometer, and then use the FEL output on the high harmonic. Sorry. To inject into a second radiator, which is again tuned to a higher harmonic of the first FEL. Of course, they're going again through a short modulator dispersive section to induce microbunching at higher harmonics of the first FEL, then radiate on these higher harmonics, and in this way we can reach up to the soft X-ray range. Yeah, 4.2 nanometers as an example here. This is already soft X-ray. So here we just get into the regime of core shell ionization. And this is then a typical output spectrum for this. It's called Fermi 2, the two-stage HGHG laser. Okay, then I promised to show a few more modern or new developments in the XFEL world. And one modern development, which is actually already more than 10 years back when this was first realized, but still this is basically a new development. So, and it all relies on using more than one undulator. Yeah, is to in this arrangement have two undulators, and why not tune each undulator to a different wavelength, and also delay then the emission pulses from one undulator with respect to the laser pulse emitted from the second undulator in time. In this, so this is a quite straightforward way to produce two color pulses, a pair of two X-ray pulses which have different. It's called color, but I mean we're talking about X-ray. So these are this is a pair of two X-ray pulses with different photon energies. Just by using the same electron bunch, so we inject one electron bunch, induce SARSE lasing. So this is only SARSE. There's no seeding here. SARSE lasing in the first undulator at one particular photon energy. Then the electron bunch is deflected across this magnetic chicane. This, of course, delays the electron bunch when it arrives in the second undulator. So here the second undulator, which produces the blue pulse compared to the red pulse in the first one, arrives or is produced in the second undulator with some time delay, which can be adjusted in this range of 0 to 40 femtoseconds. Okay, this is quite small time delay, but for some specific experiments, that might be enough to have this like femtosecond time delay between the two pulses. And this was essentially just demonstrated in this publication here. For example, with the first color tuned to 13 kilo electron volt and the second color to just below 10. And also in this proof of principle publication here, they showed that you can actually keep one color, so one photon energy of one pulse at 11.4 keV or so, while then stepping through the photon energy of the other pulse just by tuning the K2. Remember these K parameters, that's the undulator parameters. That's this constant in our famous undulator equation, which is controlled essentially just by the magnetic field in each undulator. And then by changing the K value, we change the wavelength or the photon energy. Yeah, so here you can see that the K2, in this case, the K2 here was stepped through these different values. And in this way, the photon energy of one pulse was changed in a very controlled way, or rather controlled way, while keeping the photon energy of the other pulse constant. But yeah, I mean, this is a SARSE emission. So it's not seeded, and therefore each pulse has, of course, quite a broad width of the spectrum. Yeah, you can see it's definitely not a sharp laser line. The bandwidth of both emission spectra are on the order of, what is this, maybe 0.2 KE, so 200 EV, or maybe between 100 and 200 EV of spectral bandwidth, which is, of course, quite a lot, but maybe enough for many experiments. Yeah, very much in the same way, actually, Shiva Ramakrishnan and I participated in an experiment that was done at the free electron laser, the European free electron laser in Hamburg, where also using two separate undulators with the magnetic chicane in between was used to produce two color pulses. Yeah, so the electron bunch here produces one first, let's say, red X-ray photon pulse, which of course keeps traveling along the beamline, and then the same electron bunch is injected into the second undulator with some time delay to produce a second blue pulse. But and then these two pulses are focused onto a target. In this case, the target was helium nanodroplets. This is the favorite target system that Shiva Ramakrishnan and I have been studying over many years now. And the way we studied these helium nanodroplets was by focusing the X-ray pulses on the droplets and, in that case, detecting the scattered light from every single helium droplet. So at the end of the beamline, we had a X-ray PNCCD detector, it's called. So it's just a variant of a CCD detector, so a camera essentially, that records the scattered light from individual helium droplets. Of course, there has to be a hole in the middle of this CCD camera because there's this X-ray, very intense X-ray beam of X-ray pulses that travels through that would immediately just drill a hole in the camera. So there needs to be a hole, or actually there's a gap in the middle of the CCD camera. But we're not interested in the central part of the beam. What we are interested in is to detect the light that is scattered off the helium droplets. And typical scattering image from a single helium droplet looks like this. Essentially, I mean, we will next week take a little bit closer look into diffraction imaging or scattering imaging of X-rays from single particles, nanoparticles. Just to tell you already now that for a spherical helium nanodroplet, we expect these ring structured diffraction patterns. And yeah, that's why you see these different rings here. This is essentially just diffraction of a circular aperture. And here in the corner, you see the radial profile. If we integrate over all the angles, then you get a radial profile. And what we can see in this radial profile, that's actually the interesting part. You can see both a sharp, like sinusoidal modulation, but there's also a beat note on top of this modulation. Yeah, you can see that the amplitude is large. There's a strong modulation at short angles, and then there's the modulation goes to zero, and then there's another like revival. And so this beat note is exactly coming from the fact that the diffraction was recorded for a pair of two pulses where the two pulses had different photon energies. Yeah, it's like it's just a superposition of two sine functions, like decaying sine functions, which by interference produced this beat note. So this is was the direct first manifestation of recording a diffraction image from a two-color pair of X-ray pulses. Yeah, we can then do the fitting of this radial profile with a sum of two diffraction patterns for a red and a blue photon, and that actually matches very well. But even more interestingly, this PNCCD X-ray camera has the unique property that for every pixel where light is detected, it doesn't only detect how bright, like how many photons hit the pixel, but we could even detect more or less what the photon energy was, yeah, the color. So you can see here on the x-axis, this is we call it ADU value, but essentially it's the charge produced by a photon hitting a pixel, and then this charge can be read out. And what you see is there's this peak structure. Like there's a lot of signal basically for no brightness. So this means there's most of the pixels actually did not got hit by any photons, but then there's this double peak here at a specific brightness value for the pixels. And that is exactly due to the fact that we have both red photons, which produce slightly less charge, that they produce this first peak, and the blue X-ray photons, which produce slightly higher charge. Yeah, so we could actually more or less resolve which color the photons were that hit individual pixels. So this is a histogram over all the pixels. And then, of course, there is in the central part, there is some pixels where not only one photon, but two photons hit the same pixel. That produces these peaks here at roughly twice the value of the single photon hits. And then there's events where there's three photons and so on. So this allows us to filter the data for this ADU value for the pixel brightness and actually try to reconstruct from this one image that was created by the scattering image from the pulse pairs. We could actually decompose this image into the scattering image for only the red X-ray pulse and only the blue X-ray pulse. Yeah, so this is actually the first time that people have, or we have succeeded in recording diffraction images of single particles with pairs of X-ray photon, X-ray pulses, and then decompose this into the image of, let's say, recorded if the red photon, the red pulse is the one coming first, then this is the image from the pump pulse, and then we have an image from the probe pulse. And I mean, here it doesn't look too spectacular because in the end, the diffraction image or here the radial profile, if we calculate back what the structure of the particle is, it's actually the particle seems not to have changed much by being irradiated with the first pump pulse. But in principle, by irradiating a particle with the first X-ray pulse, we would expect that the particle gets ionized and starts exploding and all sorts of dynamics happen. And then the second probe pulse will actually image the structural dynamics of this particle that is induced by the first pump pulse. So, and the great thing about using these pulse pairs is that we get from basically one camera image, we get both the information of the initial state of the particle. Yeah, how did it look like? Like, was it spherical? What was the shape? What was the size of the particle before anything happened? By taking a snapshot of the particle with the first pulse. Then we let the particle evolve, like expand or melt or explode or do something induced by the first pump pulse, and then image the final state at a specific time delay using the second probe pulse. So this is the goal that we will continue working on to really like take movies essentially of one particle as it evolves in time by being irradiated by a first X-ray pulse. So that's one development that we and others are clearly working on to use these capabilities of producing more than one X-ray pulse in the same free electron laser. Another very exciting new development that has just been realized. So this is actually, it's a preprint where you can read about this project. So it's not even published yet. But what you can, so what was realized at the European free electron laser very recently is like real laser operation for an X-ray free electron laser by basically closing or building a laser cavity around the undulator and getting real laser activity, just as so far it has only been possible in the infrared or in the terahertz regime. Yeah, remember we always kept saying that it would be nice to have a laser cavity to really get the X-ray laser lays just like a regular laser with an optical cavity around, but for X-rays there are no mirrors. Unfortunately, it's not possible to build a resonator. Well, this is actually not completely true. If you spend a lot of money and do everything right, then by using a diamond single crystal thin diamond layers for realizing mirrors, but this is not, of course, not a conventional mirror. This is a single crystal diamond, just put at the right angle such that we have constructive Bragg refraction on one crystal, and then a second crystal again, which acts as a Bragg refraction element. So it's two diamond Bragg crystal mirrors on each side, which are just good enough to reflect or refract enough of the X-ray pulses to close the cavity and to have actual laser operation. And yeah, so there you can insert a grating here and refract some of the light out for measurement purposes. And if you do so, then okay, yeah, so then let me just quickly go here. Then you can actually measure how the photodiode signal here, which is a monitor of the individual X-ray pulses circulating around the resonator, how this yeah, here in the blue, that's this seeded pulse. So this is for a closed resonator, how the power actually builds up. This is also called the ring up process, by essentially sending the X-ray pulses around in the resonator and being amplified on every round trip by just being superimposed with a fresh electron bunch, which happens to be injected into via these magnetic bending magnets here. The electron bunches, of course, have to be injected into the laser resonator just with the right timing to be well superimposed on the X-ray pulse, traveling just at the same position, essentially on top of the electron bunch to be amplified. And this has to be done repeatedly so that the X-ray pulses are being amplified up to saturation. And then when essentially the timing is varied out of sync and the X-ray pulses are no longer amplified, then we measure what's called the ring down time. So we measure an exponential decay of the X-ray pulses as they cycle around the resonator without being amplified anymore. So that's called the ring down time, or the ring down process. But yeah, so this, as I mentioned, this requires that a fresh electron bunch is injected into the undulator just at the right timing, such that it overlaps in time with the X-ray pulse that circulates in this crystal cavity, such that stimulated emission happens just at the right time and thereby amplifies the pulses on each round trip. And the round trip time of the X-ray pulse in this resonator is just given by the speed of light, and which is a constant, and the length of the resonator. So obviously the length of the resonator has to be just adjusted just in the right way, such that the round trip period matches the timing, so the time space, distance difference between electron bunches that can be injected into the cavity and be superimposed with the X-ray pulses just at the right time to amplify the X-rays. And here for this realization at the European XFEL, this was every 220 nanoseconds. So that's the round trip time of the X-ray pulses in the resonator, and it's accordingly then that's the distance in time between the electron bunches that have to be injected to just match the timing. Yeah, and then if this is all done correctly, and the X-ray pulses have the chance to get amplified in many round trips, just like in a usual laser, yeah, where you have a high quality resonator and the light bounces back and forth many times. Every time it's amplified by going through the laser medium, it's amplified coherently by stimulated emission. Then we get a very narrow spectrum, like a real laser emission spectrum, just like we know it from regular lasers. But in this case, you can see it's almost 7 kilo electron volts. So this is in the hard X-ray regime. And of course, yeah, this sharp spectrum builds up only when it is actually in this real laser, when it operates as a real laser, meaning that the X-ray pulses have to bounce back and forth many times. So you can actually, this can be followed in time. So after the first bunch, like first amplification, there is no real lasing yet, because it just it's essentially a SARSA operation, which produces this very broad broad spectrum, and no feedback yet, because it's only the first bunch. So there's basically only maybe one round trip. But then after 65 round trips and 55 times coherent amplification inside the laser resonator, then you can really follow, like on a basically for every round trip, you can see how the spectrum evolves and evolves this sharp laser emission line. And this connects back to the very basic laser physics that we talked about in the first lecture. If you remember this slide, those of you who were there and remembered this very simple model for laser activity. We have a broad gain medium, that's the blue curve. We have some loss curve, which is usually given by the properties of the laser resonator. I mean, the coating of the mirrors is usually chosen such that you have low losses, so high reflectivity in some spectral range that hopefully is just well matched to the gain profile. And you have the resonator modes, which is given by the length and the reflectivity of the mirrors of the laser resonator, which gives these transmission modes here. And all these three components have to match together such that at one allowed resonator mode, so where resonance condition is fulfilled, the loss curve just matches the saturated gain curve, right? This is what we found out from this very simple rate equation model for lasing, that in steady state lasing, the gain drops down to just this condition of gain equals losses, meaning that the saturated gain just takes the value of the loss curve at this one point where lasing is allowed, at this laser mode, and then lasing essentially is possible only at one specific frequency, meaning that in the laser spectrum, if we look at the output power spectrum of the laser, we ideally have only one monochromatic emission line of lasing. And yeah, this is now going back to the previous slide. This is more or less what people now see, only not with a conventional laser in the visible or infrared, but now with this free electron laser in the X-ray range. And this is really the first realization of an X-ray, like a real real X-ray laser, which is not just a SARSA FEL. Yeah, SARSA FEL. Remember, this can be seen as a super radiator. This is this amplification of spontaneous emission. So not really a laser, but here for the first time, like people have now built a real laser setup with a real laser resonator around X-ray amplifier. So an undulator that amplifies the X-rays, and accordingly, it's now possible to get very narrow band and very intense and very high photon energy X-ray laser emission. All right, that is all from my side. Are there any questions to this part? I mean, the references are down on the slides. You can read more details, of course, yourself by looking up these publications. So if there's no questions right now, then I would have questions to you. We now play this Q&A game again for you to have a chance to recap a bit about all we have been talking about in the context of free electron lasers. And I hope that Thanuv is there and has hopefully prepared the Q&A session. Thanuv, are you there?
Tanu is not attending today's session. Have you sent him the questions by mail?
Yeah, I did. And he actually confirmed that he wanted to prepare the Q&A session, but obviously then he didn't. Then I would say no problem at all. Maybe he will be there in the next session, which we will have. When is the next session again? The day after tomorrow,
On
on
Friday, yes.
9th, on Friday, yes. So then no problem. We'll just postpone the Q&A on free electron lasers topic to Friday. And then today we will proceed with the first paper presentation given by Wishwas and Sumia, right? Is Wishwas and Sumia there?
Yes, sir.
Are you ready with your
Yes, sir.
presentation? Okay,
Yes, sir.
perfect. Then I stop my screen sharing and we will learn something about attosecond pulse generation in free electron lasers. I hope.
I'll share my screen.
Yes, please.
So are you able to see the presentation?
Yes, but it's not presentation mode yet. Yes, okay.
Yes, sir.
All right, yeah, then please go ahead and tell us a bit about attosecond pump and attosecond probe spectroscopy.
Yes, sir. So today I and Vishwas will be talking about the very first talking about the paper in which it was the very first time they did the all attosecond pump probe X-ray spectroscopy on liquid water. And basically I'll be talking about so giving an outline. I'll be sharing with you the motivation on what led to this experiment, and thereafter Vishwas will follow up with the methods that were used, that is the X-ray free electron lasers were used in the X-sleep mode. So Vishwas will be telling about of it the X-sleep mode explicitly, and about the experimental setup as a whole, relating it with whatever has been taught in the class. And after that, I'll be talking about the findings and the conclusion uh, of this paper. Sorry, I'm unable to change. Yeah. So basically, before getting into the motivation, since this experiment is based on the spectra of water, so I'm going to talk about the orbitals that are present in water that usually present themselves or manifest themselves in the spectra. So in water, we have H and O, of course, and the molecular orbitals of water are usually formed due to the mixing of the atomic orbitals of O, such as 2s, and the 2px, 2py, and 2pz. And with those of H, there will be two H1s orbitals. So those mix, and thereby it gives us the following molecular orbitals, that is 1a1, 2a1, 1b2, 3a1, 1b1, and there will be a 4a1. 4a1 is essentially an antibonding orbital which is unoccupied. And for us, what will be relevant for so essentially 1a1 is so we have, even under 1a1, we have the oxygen's core level, that is the 1s1 level, and that doesn't participate in the molecular orbital formation, but that is quite extremely relevant for this experiment. So mentioning that is important. And what other molecular orbitals that are relevant would be the 1b1 molecular orbital. And basically, so over here we'll be talking about two kinds of spectra. One is the XCS spectra, which was done before on water before the all attosecond pump probe spectroscopy, and which actually it was through the XCS spectra that we encountered a particular sort of a dilemma in water, which was cleared by this all attosecond pump probe. So I'll be talking about that. So in XCS, essentially you have a X-ray photon source, which the X-rays come and they knock out the core electron that is there in the oxygen 1s orbital, and thereby that electron, so the hole that is formed over there, the vacancy which is there, that one is filled up by the by either of the electrons present in the above molecular orbitals, and that leads to the emission of a photon, which leads to the XCS spectra. And in case of our pump probe spectroscopy, I'll be talking about it a bit in details in later, but giving some idea about it is basically over here the pump, both are pump and probe. They are X-ray X-rays, and the pump is essentially of the energy of around 200 electron volts, whereas the probe is of higher, it's almost 500 electron volts over here. So basically what happens is the pump comes in and it ionizes the electrons from the valence orbitals of our water, and when the probe comes in, it is through the absorption of the probe that the probe pulse that the electron from the core oxygen, it goes and occupies this, leading to the absorption spectra. So in case of XCS, so basically the history of XCS, this is the XCS spectra that was found, and in the XCS spectra we have the emission peaks due to the 1b2 the molecular orbital, due to 3a1 molecular orbital, and in case of the 1b1, where we should find a single peak, we rather got a doublet, two peaks, and that again that was the reason for the dilemma. Like it was quite unclear why 1b1 is leading to two peaks, and I should mention that it is very important. And why is it important? It will be clear later, that the XCS spectra is generally measured using a synchrotron radiation, which has a very good energy resolution, but it has very low time resolution, like it is of the order of greater than 100 picoseconds. So this will be important later, because it will tell us why attosecond was important. So this doublet actually led to two theories, and those theories were that the theory number one was that water essentially exists in it's not homogeneous, it doesn't have a single structure, but it exists in two structures. That is, one structure it is quite ice-like, that it has tetrahedral structure, and it has a strong H bond ordered around it, whereas the other structure is more disordered and it has weaker H bonds. So this sort of a theory led to people thinking this sort of a theory was relevant, mainly because this theory originated from the explanation of the anomalous properties of water. Like water, usually for a normal liquid, density should increase as we go down in temperature, like as it goes towards a more solid-like state. But for water, the density peaks at 4 degrees Celsius, after which it actually decreases. So such sort of a anomalous sort of a property that was shown by water, that led to such structural led to this two structure theory, and that was again related to this 1B1 doublet also, that water in liquid form also, it lies as a mixture of these two structures, and it is because of the presence of these two structures that we get two kinds of peak. Whereas there was another theory which also came up, which was way different from this structural. So in case of a structural, if you have two structures, it is quite evident that for us, it doesn't matter whether what is the time resolution that we have in our spectra. As long as we have two structures existing, uh, it will always, whatever may be the time resolution, it will always lead to two peaks. But then came up another theory which suggested that in case of water, what happens is that when we are knocking out the oxygen core electron, it is creating a hole, and that hole has a lifetime of 4 femtoseconds. That is, it takes about 4 femtoseconds for the electron to come and fill it up. So in between these 4 femtoseconds, this hole creates a sort of a electric field environment around it, which causes the protons, that is the hydrogen which is associated with the O, to stretch, the bonds to stretch, as a result of which this is causing shiftings in the energy levels, which is leading to two peaks. So when we are taking XCS, where essentially it's an average over a larger amount of time, so within this timeline you are getting two sorts of what do I say, two sorts of things happening. One, that is the energy levels have shifted, and one when the energy levels haven't shifted. So both the peaks are presenting themselves, and therefore you have two peaks. So to know the exact mechanism, which of the mechanism is actually which of the mechanism is actually correct, we need a sort of a time resolved method which will actually freeze the proton dynamics, that is, which wherein we go into the attosecond sub femtosecond regime, that is in a regime that is less than this 4 femtosecond, and over there we can then freeze the proton dynamics and thereby see whether it is actually happening due to the proton dynamics or due to structure. So this leads us to the all attosecond pump probe spectroscopy, and Vishwas will be next talking about the experiment as it is.
Yeah. Thank you, Soumya. Yeah. So good evening to all. So yeah, before going into the what we actually observed in the experiment, I'll just to take some few slides to explain what the setup looks like. So the basic layout of the setup is this. So basically, we have this one LCLS, that is a linear coherent light source XFEL laser operating in the X sleep mode. X sleep stands for X-ray laser enhanced cytosecond pulse generation. And we also have the split undulator, meaning we have two undulators in order to generate the pump pulse, which is the omega pulse, and the probe pulse, which is the 2 omega pulse. And in order to create the delay between these two pulses, the delay is around 600 attoseconds. We use this matrix chicane. And then as a target, we have like a liquid water sheet jet. And in order to study the spectra, we have a X-ray transient absorption spectrometer. This is like a 2D detector, which gives a plot between, in the x-axis you have the photon energies, and in the y-axis you have the spatial profile and the intensity profile. And then you have the gas moderators and gas generators for short-to-short diagnostics. So there's a basic outline, but as you can see, the undulator is actually the very heart of the setup. And since we have been studying about undulators and XFEL lasers, we just thought, it would be a nice, like a quick, we can just take a quick detour to see, just like with a quick recap of how undulators and XFEL free electron lasers work. So yeah. Can you see the slide? Yeah, thank you. So yeah, basically an undulator, as you can see in the diagrams, it's just a long periodic array of magnets with alternating polarity. So these undulators, they basically force an electron to execute small transverse oscillations. And these oscillations, during the oscillations, the electrons are accelerated and decelerated, and they emit this synchrotron radiation. And this radiation, it actually interferes over long periods, and when they interfere constructively, they emit this radiation of the orders of lambda, which is given by the undulator equation lambda by lambda mu by 2 gamma square into 1 by k square by 2 into gamma square theta square, where lambda u is actually the order, the period length of your undulator. K is your undulator parameter, which is basically the magnetic strength, and the gamma is your Doppler shift, and theta is your off axis observation angle. So by weighing the K, you're actually seeing this undulator operate in two modes. One, if K is way less than 1, then you won't see large oscillation. You will see very small transverse oscillations, which can lead to very narrow band and coherent radiation. You can see emission of narrow band and coherent radiation. But let's say if you increase the magnetic field, then you will see very large oscillations happening. This may not exactly lead to constructive interferences. So this actually leads to incoherent and broadband emission of radiation taking place. So this is actually very clear in the plot, in the brilliance plot, in brilliance versus photon energy plots, where you can see at the very top, you can see for the undulators, it has a very narrow band, but the brilliance is very high. The brilliance is basically for the photon flux per phase space per bandwidth. And you can see at the very below, you can see the high superconducting magnets, bending magnets, and you have the Wigler and so on. Okay, of course, the broadband, but the brilliance is relatively lower. So, can you see in the slides? So still now the undulators are not exactly beaming as lasers as such. There's just emitting radiation from electrons, which are basically they don't have any fixed phase relationship. They're all out of phase, and you don't see any gain happening. You don't see any amplification or source happening, or you don't see any positive feedback there. So it's not exactly behaving as laser. But if you wanted to exhibit some of this laser behavior, if you may, so then we have to somehow induce there should be some photon and electron interaction should happen. So so in X-ray photon lasers, that is what's happening. So basically, you have your emitted synchrotron radiation that is interacting back with the electron with your electron beam. So then what happens is that basically you can see there's this process called as self-amplified spontaneous emission, which is called as SASA, where basically due to some density fluctuations, which can classified as a short noise, these small density fluctuations, they try to within the electron beam, they try to emit like a radiation at the wavelength matching the matching lambda L, which is the which is the undulator resonant condition. Again, if a small amplitude emission happens, this small, due to the short noise induced small serial radiation, if it interacts with the electron beam, this actually, depending on the phase difference, they can either, transfer energy from the beam to the electron, from the electron beam to the radiation, or from the light to the electron beam. So basically, depending on this, you can either see some electrons gain energy and some electrons lose energy. So this actually creates like a sort of like a energy modulation, if you can call it. And due to some electrons gaining and losing energy, you can see some electrons slowing up, or some electrons like slipping down, and slowing down also, or like speeding up. So this actually what is created is that this in turn creates like a density modulation, where you can see these electron beam getting micropunched. which you can see in this diagram here. And after this microbunching happens, each microbunch, the electrons within each microbunch are actually all in phase. So they all are in phase. Again, the phase they're in the fixed phases of the emitted radiation, and their spacing is equal to the wavelength of the emitted radiation. So this process keeps on happening. So again, you have due to this, you'll have again radiation emitted, and that radiation again interacts with your electron beam, and this keeps on happening. Then you see a very exponential gain. You see at the below plot, you can see the how much gain you're seeing. So as the micro bunching becomes so prominent, you can see more gain happening. So you can see more amplification happening. So this is how, in a way, you can go from undulators to XFEL electron lasers. Can you change the slide? So that's basically how, this is just a quick recap of how undulators and XFEL electron lasers work. And now this coming back to our setup. So you can see in the bottom right, you can see the actual this setup, the Hall X-ray high-density transient absorption spectroscopy. And here at the starting, you have something called as X-sleep electron beam. So that X-sleep electron beam is actually, if you go to the X-sleep operation, you can see at the initial you have the electron beam going through a wiggler, and then it goes to a to that chicane. So in the wiggler, what happens is that due to the wiggler having large magnetic fields, you see very large energy modulations happening. And this large energy modulations, it actually goes through a chicane where you can see the density modulation taking place. And this emits a very high density electric current spike. So this high density electric current spike is what goes into our AX80A setup. So this is what we use, this is what we use for the first and the second and later. So in a way, this what we're seeing is not exactly in the first and second later. It's not exactly SASA. It's actually enhanced SASA, because we actually sending in a very specially prepared beam inside. So due to that, we're actually seeing more enhanced enhanced X-ray pulses being produced. So the first generator is actually tuned to omega pulse. So you'll actually get the omega X-ray attosecond pulses out of the first generator, and and so some of it actually goes straight through, and some part of it actually goes to delay chicane. Where this delay chicane, unlike the one in the X-sleep, this is only to create a delay, or like a certain delay between the omega and the 2 omega, between your pump and your probe pulse. So after it goes to delay chicane, there'll be a delay of 600 seconds, and they actually send to the second indulator where it's tuned to it's tuned to 2 omega. So then now you have your pump and probe pulse, which are tuned accordingly, and they're spatially, they're spatially overlapped on the same part of the water jet. So can you change the slide? Yeah. So basically, you have these pump and probe except pulse with a spatial overlap, and they're focused onto the same area on the water jet. So basically, like the pump creates, in the valence shell, it actually creates an ionization. So it basically electronically excites the system, and then your probe, it basically when it travels to the same region, it tries to induce a core to valence transition, and based on the energy absorbed in order to make this valence to core transition, we can see how the probe is we're basically seeing how much energy is lost in the probe. We can actually judge what kind of transition is happening. So this is how the transient absorption spectroscopy is actually takes place. And then you have gas phase intensity monitors to record pump and probe energies on every shot. And basically, not to find the delta A, basically the energy difference, in order to cause it core valence transitions, you actually have the pump off signal as your reference, and the pump on as the one where your probe pulse loses energy, and you are able to calculate and and get the proper transient absorption signal. So this is done using a 2D X-ray detector where, in the X-axis you have your photon energies, and your Y-axis you have your spatial and intensity profile. So this is how you are able to do this, transient absorption spectroscopy using at the second X-ray pulses. So that is all from my side. I'll ask Soumya to finish it up with the results which they found. So yeah.
Okay, so for the results, I'll be getting into the delta A spectra, which was mentioned. So as you can see over here, we have the delta A essentially is the difference between the absorption by the water molecule, probe absorption by the water molecule in the presence of the pump and in the absence of the pump. So that difference leads to what we can see over here. This is the sorry, yeah, this is the delta A spectra that we have, and what we can see over here are three prominent features that we can see. There are two positive peaks and one big negative peak. The positive peaks are at around around 525 eV, and the negative peak is around 535 eV. So if I go back to the X-ray spectra that we have, so in the X-ray spectra you can see around 525 EV. Near about that we have the 3A1 and the 1B1 peaks. So over here the positive peaks that we have, they both actually correspond. The left one corresponds to the 3A1 and the right one actually corresponds to the 1B1 peak. Now the important thing, the very important thing to see over here is actually 1B1 is not a doublet, it's a singlet, and there's just a single peak over here. And apart from that, we have this negative peak. The negative peak is essentially coming, it's again another feature of the pump, which although not relevant, still I can explain. Like it's due to a change. So since we are taking a difference in the absorption, so what is happening is that this negative peak is coming because there was an absorption which was happening when the pump was off, but now that absorption is not happening, and that happens uh, because when the pump comes in, there's a lot of water molecules that are getting ionized, and so if we have one water molecule and there's another ionized water molecule beside it, so that ionized water molecule will create a electric field around this original water molecule, which leads to a shifting of the energy levels, which is why at 535 when we exactly actually expect one of the absorptions. Okay, so I forgot to mention, so the absorptions actually lead to transitions from the core to the valence orbitals. So since the pump is coming in and ionizing our 1B1 or 3A1 or 1B2 electrons, so basically when the probe comes in, this core electron essentially excites itself to either of these orbitals where there is a vacancy already. But there also lies above that, when I mentioned in the first slide that there is the 4A1 antibonding, which is the unoccupied orbital. So so it is quite possible that due to the probe, the electrons from the core can go into the unoccupied orbitals. So it is this unoccupied orbitals which actually get shifted due to the ionized water molecules, due to the electric field created by the ionized water molecules, and therefore you see a negative peak, because when it was not ionized, there was an absorption, but now there is none. But coming back to the main feature of our experiment, the 1v1 is actually a singlet, which is again given what we had, given the motivation that we had presented, that we need to get into the time scale where we are not seeing the nuclear motion, but we are rather just seeing the electronic motion happening due to the excitation due to the probe, and that electronic motion is creating just one single transition from the core to the valence 1b1, which is also confirmed by a theory. So there are basically, this paper presented two theories. It didn't get into the details of it, but these are molecular ab initio molecular simulations. Ab initio molecular simulations, and it presented two such calculations done by two such theories. And the theories suggest that in the 0 femtosecond time, when we have just we can see there's just a single peak, but in the 4 femtosecond time we are again getting two peaks. So basically that again is around this 525 EV region. So that confirms that it is due to this it is due to the nuclear motion, that is when due to the ionized uh, core electron, there is a electric field which is causing the protons to repel, and therefore there is a shift in the energy levels. And it is because of that there is the appearance of two 1v1 peaks, and not due to the existence of two kinds of structural motifs in water. So this was really important, because there was this long-standing dilemma regarding this 1v1 doublet, and this being the first all attosecond experiment wherein it went to that sub femtosecond time scale. It was this clarified that dilemma. uh, yeah, so that's it from my side. Thank you.
Yeah, thank you very much. Very nice presentation. Yeah, so we see that free electron lasers cannot just be used to demonstrate that attosecond pulses can be produced in the X-ray regime, but this is actually even useful for doing experiments that provide very important information. In this case, it was like in the water system, like a physical chemistry problem, but of course there's many other applications in condensed phase, like solid state physics and other systems that are conceivable, where these extremely short, high time resolution attosecond pump probe experiments now would be very interesting, very instrumental. Are there any questions? Then, I mean, if maybe people still need a few more minutes to digest, I would have one question regarding this XLEAP method. Could you please just, yeah. So I was wondering, this energy modulation that eventually leads to this density spike that generates the attosecond pulse. How exactly is, or can you explain maybe once again how this looks like a single cycle modulation of the electron bunch? And like in this wiggler, it looks like there is there is some radiation present in the wiggler. Is it an external laser pulse that's overlapped with the wiggler, or do you?
No. So based on my understanding, so since it's a wiggler, so what happens is that it's actually producing this very broadband radiation is producing from the electron beam from the source. It's producing this broadband radiation, and that the sense is also the wiggler is also producing this very large energy modulation as well. So you have a very large broadband radiation coming out, and that broadband radiation you're actually trying to put it into the chicane, where it's based on the it's actually creating this energy dependent path differences, which actually further creates this density modulation. So, so after you actually create a density modulation, you're seeing this is one very intense, very high density this current peak you're seeing. So based on my understanding, that's all that's happening there. So it's broadband, but it's very intense, high density electric current you're seeing in that. So yeah.
Okay. Okay, thank you. Any more questions or comments to this presentation? Okay, I mean, it seems everything is clear, or everything is unclear. We don't know. But I found it quite very clear. I think you did a very good job in both introducing the general concept of the experiment, like the level structure of the water, and explaining this open question that was addressed, and also you did a good job in recapping the basic XFEL science, and in particular, and then building on this, introducing this XLEAP method. So that's very nice. Thank you very much. Any more questions or comments? Then now would be the time. If that's not the case, then thank you very much for this presentation. And I mean, I'm done for today too. Then we will just stop here today and reconvene on Friday. And then we'll have a little Q&A session on Friday, and we will have more presentations, namely there will be 2 paper presentations about another imaging technique using XFELs, which is called Coulomb explosion imaging. So Pratik and Rajni will then tell us about these Coulomb explosion imaging experiments on Friday. So thank you very much for joining, and we'll